So welcome everybody and thank you for the invite here. We actually just had a two-day computer vision AI workshop with Siemens Energy at this very location. Also with Voxel 51 involved with a talk, so thanks for that and a small hands-on session. And now we were invited to give a talk here at their meetup. So I was quite happy to see Sebastian's talk because it's quite related to mine. I'm also going to talk quite a bit about defect detection, but we're going to move from an indoor scenario to an outdoor scenario. So at Siemens Energy, we have a product that is about inspecting overhead lines. So let me see if that works. Yeah. So overhead lines there are currently a lot of challenges regarding overhead lines and overhead line inspection. So obviously, there is increasing energy demand currently, and also there is the integration of renewable energy, which is a great thing, but it also poses a lot of stress on the grid because renewable energies are coming in large fluctuations, depending on when the sun is shining, when the wind is blowing, and so on. Also, the infrastructure is aging, and it is a challenge to build new infrastructure. You cannot just build a lot of power lines all over the place. And also the impact of extreme weather is getting worse. So there is an incentive of keeping your grid stable and in a good condition and to monitor it consistently. So how does this look like today or in the past, let's say, up until today is generally there are regulatory mandates that the grid needs to be inspected. So at least here in Germany, for example, every 2 years or so, you need to make sure that your grid is undergoing some kind of inspection. And quite often these inspections are relying on ground crews or on manual tower climbs or are done like by binoculars, people walking through the electrical power line, through the corridor and just looking if everything is okay. Also, they are done with helicopters from the air, like you can see an image here where there are people like with binoculars sitting in the helicopter and checking if everything is okay. And more recently, this is also done with drones. The problem is that findings are often only documented manually. There is no real digitalization or no traceability of these findings. And of course, the human eye misses a lot of things, especially when it's tiny things like a crack on a conductor or a crack on an insulator, for example, can easily be missed by flyover and the human inspection. So at Siemens Energy, we have been working in quite an international team, actually. So I come from Graz in Austria, but we have a very multinational team. And we have built a smart remote sensing platform for overhead line inspection. So in my talk, there will be not much about, or nothing probably about LLMs and agents and so on. It's really a lot about classical computer vision. There is AI involved, of course, but you will see how many different topics in the field of computer vision will come together in such a system. So what we do, we have a helicopter, and on the helicopter there is a sensor pod that we built with a team in Nuremberg. And the sensor consists of a LiDAR scanner, so a laser scanner, multiple RGB cameras, up to 20 actually, because they are looking in different directions. And there's one for looking on the ground, on the corridor. There's one forward, backward, sideways, and multiple different angles. There's also an infrared camera to detect thermal hotspots and a UV ultraviolet camera for corona discharges. I will not talk about everything because it's really a lot, but just to give an overview what we do with this platform. So first of all, there are GIS products like orthophotos, terrain models, vegetation, distance layers, and stuff like that. So map layers, like you see on Google Maps, for example. And they are used by our customers to assist them also in the planning of power lines or when they rebuild something, for example. A second pillar is the digital twin feature or the inventory list. So the LiDAR point cloud gives us the option to build a 3D model of the electrical power line, and we detect and inventorize all of the relevant components on the line. For example, insulators or vibration dampers and clamps and joints and marker balls and bird diverters and whatever is there. And the third pillar, which is what I will talk about mostly, is the defect detection. So what I said in the beginning, like you want to make sure that your assets are in a good condition. So we have quite a comprehensive solution for finding defects on your power line. It's all a bit small here on this slide, so I will show it obviously in more detail. So on the left, you see our sensor head with all the cameras. On the right, it's an overview picture with the helicopter. I already mentioned the sensory, the components. Bottom line, what I want to make here is we capture a huge amount of data. And my talk will be mostly about what does it take with AI and computer vision to go from a, let's say, demonstrator, proof of concept, textbook kind of problem to a system that needs to work for tens of thousands of kilometers of power line data. So it's more from the practical side on what do certain performance metrics even mean when they are applied to a huge data acquisition. So we're capturing around 300, I'm not sure if this number is still exactly up to date, but several hundred gigabytes of data for a single kilometer of power line. So this is just, I mentioned this already earlier, that what we're doing is not just AI and not just training models and applying models. There are a lot of different fields involved to build such a remote sensing platform. So it starts with the LiDAR scanner. You need to do strip adjustments. So we fly on both sides of the line with a return flight. So you need to align these 2 point clouds. You need to calibrate the whole system, all these cameras to the LiDAR sensor and so on. You need to have a lot of knowledge about 3D computer vision, triangulation, projections, and so on. And of course, there's also the machine learning part, like you detecting all these components with an object detector, detecting anomalies, a lot of, let's say, few-shot learning, learning from limited number of samples, because defect components are very rare, obviously. And of course, with these amounts of data, it's also a lot about ML ops, a lot about how do you process the data on a huge cluster, or do you go to the cloud? And so there are many, many aspects that are involved. Here, just a few pictures so you can imagine what this looks like. So here you can see the point cloud. It's a classified point cloud, so we also have AI models that classify every point in the point cloud. For example, red is conductors, yellow is tower, blue is insulators. Here you can see buildings, because we also need to measure the distance from buildings to power lines, because there are regulations what these distances need to be. On the top right, you can see our vegetation distance feature. So we need to detect if vegetation grows too closely to the line, because it can cause a wildfire, for example, if it touches the wire. We also do simulations of wind swing and ice load on the conductors, because the static scenario, it might not cause the wildfire, but if there's wind and it swings the wire, then it might hit a tree, for example. So there are many interesting use cases. Before I go to the defect detection, the other major thing where computer vision and AI is involved is this inventory generation. So here we start with single images and we apply object detection. That's pretty standard. So we train detectors. We have huge amounts of data, so it's not a problem to just annotate a few tens of thousands of insulators and spacers and clamps and whatever you have. But the challenge is the customers do not need image-wise boxes, so that's not useful for them. They want to know how many insulators do I have on my pylon and what's the configuration, how many are in the lower layer, on the second, on the third. That's why we have the 3D computer vision aspect. So we merge these bounding boxes in the 3D space on the point cloud. So there is this 3D consolidation approach that you can see on the right. So here we move from a single bounding box detection to an actual object instance in 3D. And that's then actually the valuable information for the customer. And then to the second part of my presentation, which is the inspection. So similar to what Sebastian was showing, we also need to find anomalies in the data. So if you look closely, I mean, the larger image on the lower left is our web interface. And here you see a defect that was found. It's a glass cap insulator. And if you look closely, the lower one of the two is missing one of the glass discs. This can happen, for example, if water gets trapped in a crack and then it freezes and then it cracks or something like that. There are also other kinds of anomalies. There can be bird nests on the pylons that should be removed. There can be broken conductor strands, like you see on the lower right. There can be chippings, contaminations on the insulators. There can be these vibration dampers. So the upper left image shows a vibration damper. Next time you see a power line, you might recognize that. It's a component that ensures that the power line does not swing in a harmonic wave when it's windy. So it dampens the vibrations, as the name suggests. Second image is moss infestation. Corrosion, rust is also a similar topic. So there are a lot of things to detect on power lines. I want to walk you through what we typically do in one single example to not make it too broad. I want to focus on one example, which is the detection of broken conductors. So a conductor is made of a lot of individual strands, like you can see in this schematic image here. And it can happen that one of them breaks or multiple of them break, and then they unwind. And that can pose either a hazard, like you see on the images here. This can be pretty long, like we have seen some that are like 10 meters, almost reaching the ground. So you can maybe even electrocute someone or touch again the trees and cause a wildfire. Or yeah, if too many of them break, like in the lower right image, it might even happen that the whole conductor breaks and the system fails. So this is a classical example because it's a needle in the haystack kind of problem. So we have so many thousands of kilometers of power lines, but almost never you see such a situation. And if you see it, then it looks different every time, like you can see on these pictures. So that's a very challenging task for AI. Go ahead. So now a little bit of statistics, and that's one of the main messages I want to convey is when you work with AI models and you talk about evaluations and percentages and recall and precision, then often you just aim for some number in the high 90s. You say, oh, 97%, that's a good model, let's deploy it. But we really need to think, what does this number mean in practice? So we have up to 10,000 close-up images per kilometer of conductors. So we have many cameras, there are many conductors, we have close-ups, so we just need a lot of images. We have 2 flights back and forth. So if you have a model precision of, let's say, 97%, then you will get 300 false alarms per kilometer. So that means as a human QA person, you need to click through 300 wrong issues, and that doesn't really help you. Maybe it starts at 99.9% where you click through 10 of these per kilometer, and maybe that's doable. That's where it starts being useful. Yeah, same example with this meme. Like if you have like you test positive for a disease, the test has a 97% accuracy, but the disease is very rare, then you're probably going to be safe because most of these will be false positives. So that's also another reason why we use this 3D approach with the laser scanner and all these images and multi-view geometry, because we want to use consistency across images. So if I go to the next one, most of the false alarms happen because of unfortunate backgrounds or situations. Unfortunately, you cannot really see it here, but on the left image there is like a line on the road, on the surface of the road. And the second one, there is a wire on the ground for some animals on the farm. And the third one, there are just some trees, some bushes that have the same colors like the conductor. So the model thinks this is a strand of the conductor. And this usually leads to these false alarms. But the fact that we fly in both directions gives us two completely different backgrounds when we look at the same piece of conductor. So just that fact alone reduces the likelihood of a false alarm enormously. So if you have two independent observations with 97%, you end up at 99.9% precision. Our system is more complex than that, so we have like many images for every piece of conductor, so we can apply a voting scheme where we then can balance recall and precision. On the lower right, you can see how this looks like. Probably not so easy to imagine, but this is the LiDAR point cloud of the conductors, and the color just gives you how many votes got accumulated at that 3D position from the 2D boxes that were projected onto the point cloud. So we do some non-maximal suppression and find the true location. Okay, that's how to improve precision. How do we improve recall? So if we have this voting system and we need to be very, very sure that it's an actual defect, how do we make sure that we find all the defects, which is equally difficult? So what we already heard with Sebastian, and I fully agree with your statement about synthetic data, it's really useful to bootstrap something. It's not always useful as a replacement for actual data. But what we did, we knew on our power line there are certain damages, but we have 10,000 kilometers, we cannot look for them manually. So we started with synthetic data, like here on the upper left, you see a colleague destroying an actual insulator in front of a green screen, and then we placed that insulator into actual backgrounds. Or in the second example, we just photoshopped some things, like we removed the disk on an insulator. More advanced methods, obviously, we use like then some Blender or some rendering engines to create like fake kind of defects. I was doing this recently for the broken conductors. So here I just implemented a simple computer vision algorithm that finds the line, and then it just draws a line of a similar color in a kind of wobbly random path away from that line. So maybe you can see it here. On the right image, on the second one, you can see there is like a fake kind of strand that I was generating automatically. But the main thing that we do here, if we only add the synthetic damages, then the model will fixate again on the background because the broken strand is a few pixels. It's minimal with respect to the rest, and the model will just learn green grass means damaged conductor. So what we usually do is we also add the same synthetic image without the synthetic damage, and then the model can learn to focus on what actually matters, on the few pixels that are different. There are more advanced methods to do this. It's just a simple pragmatic approach that we do. And then you can see on the right, we have a lot of these synthetic samples on the top, but then with those, we trained the first model, and we had a lot of false alarms, but we got quite a few real examples, and with time, the real ones got more, and we didn't need the synthetic ones anymore. So there is the other problem of reducing false alarms again. So this is also tackled with synthetic data to some extent. So we can just take the false alarms and feed them back to a training. That's the obvious approach. But again, then you have a lot of empty images without a broken conductor, and the model just learns that most of the backgrounds just mean it's fine. So again, here we apply the same strategy of making a pair. Like we take the false alarms, create synthetically a damage, and then add the pair to the next training. And another interesting approach is to use explainable AI, so methods like RedCam, for example, where you can visualize which pixels actually led to the detection that the model made. And this helps us also to understand if the model focuses on the background or on the actual damage. And here you can see that the model focuses not on the full broken strand, but just on the area where the broken strand goes away from the main conductor. So that's exactly what we want, a model that doesn't just find wobbly gray lines, but actually understands this context of it, that it's near the actual line. We also had an interesting example with ceramic insulators where we needed to find small chippings And explainable AI showed us that the model actually thought this insulator is broken because it has these rings attached to it. And then we found that in our training data, most of the broken insulators had rings and the other ones did not. And the ring is obviously much more obvious than the tiny white dot. So we needed to fix the data set, add more images with rings for the intact ones, and then we could confirm that the next model was looking at the damage. Also, I want to mention that other methods are sometimes useful for training AI model, or for preparing AI models. So often you do not have data to begin with, but you can come up with a simple strategy to find data more easily in the vast amount of data that you have. So, for example, for the broken strand detector, we also trained, we did not train, we actually created an algorithm that just goes through the LiDAR data, through the lines, and then looks for points, LiDAR points that deviate from the line. So then we found also these, I don't know what this is, maybe a shoe or something, but we also find some broken strands because some of them are visible in LiDAR. Some of them, the laser beam hits sometimes the broken strand. And that helps us also to find some new data for training. Or here we started with some simple contour finding algorithm to find cracked marker balls, for example. So to summarize, or maybe to give a few more thoughts, when you evaluate models and they have a good score or something, it's always important to put it into context of the problem you actually want to solve. So what does this score mean for you, like for your problem? Is it enough or is it useful? That's sometimes something which is often like a bit not discussed enough. Like just the score is high and that's good and it's better than last time, but does it actually solve my problem or not? Generalization is very important in an outdoor environment. So there are many, many different conditions, sunlight, fog, whatever. And also generalization in terms of infrastructure. So we have to expect the unexpected. So a power line pylons can look like arbitrary almost. And this is something you really need to focus on with explainable AI, with verification methods, and so on. This also goes hand in hand with expectation management, which is very important. So if you say I have a detector that finds insulators, then you need to make sure, okay, it's insulators on steel pylons, for example, in Europe, like to make clear what is actually trained. And what I really want to emphasize is this benefit of having multi-view geometry, like not just a single image, a single detection, but actually a set of images with 3D consolidation that gives you a much stronger response. Yeah, I think that was everything. Yes, so open for questions.